A series of lectures by Professor George Phillies, based on his book, Phenomenology of Polymer Solution Dynamics, Cambridge University Press, 2011. And stand by for our forthcoming lecture series, Statistical Mechanics, Introduction to Mechanics, Harmonic Oscillation, and Game Design, based on Chapter 6, Segmental Diffusion. This chapter treats methods that are sensitive to the motions of individual chain segments of a polymer chain. The three major methods under consideration here are depolarized light scattering, time-resolved fluorescence relaxation, and nuclear magnetic resonance. The techniques are different in their sensitivity to different timescales. They are different in the molecular characteristics you have to have in order to get a signal out of the system, and they differ somewhat in what they tell you about chain segmental motion. Depolarized light scattering arises because the component monomers of a polymer are not simple spheres. If you illuminate them with polarized light, you excite a dipole which can be other than parallel to the field of the incident light. The dipole re-emits light, dipole emission, and some of that light will come off depolarized with respect to the light incident originally. Because the molecules and their parts are moving, the amount of depolarized light scattering fluctuates in time, and the characteristic time in the fluctuations corresponds to fluctuations in the position of the scattering objects. In time-resolved fluorescence relaxation, what you have to do is to label the polymer chain with a fluorescent dye. The fluorescent dye is incorporated organically through covalent bonds into the polymer chain, usually in the middle. You illuminate the molecule with light that brings it up to a fluorescent state. The molecule or its fluorescent dipole migrates in time, and therefore some of the light re-emitted by this fluorescent dipole comes out not with the polarization you'd expect if the molecule were stationary. Finally, nuclear magnetic resonance reports on the motion of individual chemical bonds over time. The first question you reasonably ask is, what is moving? What molecular motions are you actually seeing? Studies of the VH spectrum some time ago demonstrated that the relaxation time is independent of the polymer molecular weight, except for very short polymer chains, and is independent of the scattering vector Q. One can understand these two results if one is seeing measurements of motions that are not at all diffusive translationally, hence the Q to the zero dependence, and that are sensitive to the motions of very small parts of the molecule, hence the lack of a molecular weight dependence. For time-resolved fragment fluorescence, the scattering object is an organic molecule, organic component that you've stuck into the middle of the molecule or on one chain end. The organic molecule has a known dipole direction. As it rotates, because the chain is moving, the dipole direction changes, and one expects this contributes to the time-resolved fluorescence. Finally, nuclear magnetic resonance is very well understood, and what you are seeing is the reorientation of chemical bonds, which one can measure with a standard NMR instrument at a small number of frequencies in a given experiment. Depolarized light scattering readily gives a relaxation time, tau. One finds experimentally that tau increases with increasing polymer concentration. However, there is a dramatic change in the slope, d tau dc, that appears at a polymer concentration of approximately 300 grams per liter. First, we consider how chain motion, local motion, is sensitive to the local viscosity. We get this information out of fluorescence relaxation. We've inserted into the chain a submolecule, a monomer, whose dipole is parallel to the chain axis. It's relaxed by local chain rotation. The way we can change the viscosity is to change which solvent we're in, to change the temperature, to change the pressure. Gee, that's a lot of changes, but the changes are found to be consistent with a generalized Kramers relation, tau proportional to eta to the a, exponential factor is indicated. The original Kramers relation would have said that tau was proportional to eta to the first, not eta to the a. Kramers used the assumption that the drag coefficient was linear in the viscosity. There are also factors as you change solvent temperature and pressure which are compressed into that exponential, which has an activation energy E sub A and an activation volume in some sense V. Those three parameters between them actually cover a great deal of experimental ground. Of course, you could also change the viscosity by changing the chain concentration. This slide shows results of Punchard and Adolph on center-labeled polyisoprene. By changing the solvent, the temperature, and the pressure, a wide range of different viscosities, horizontal scale, were obtained. However, all of the dependencies on temperature and pressure and viscosity are reduced to three parameters. There's an activation energy, E sub A, there's an activation volume, V sub A, and there is the power to which tau depends on the viscosity, eta. At low viscosities, tau is linear in eta. At large viscosities, tau depends on the viscosity eta as eta to the 0.55 power. You notice there's a clean transition between the linear behavior, which has a small eta goes to zero intercept, so the line is slightly curved, and the higher viscosity power law eta to the 0.55 behavior. That transition is quite uniformly seen. Now, this is described as a generalized Kramers relation because it's not eta to the first. However, in fact, if you compare with the results of Heber-Green and others, studies shown in the previous slides on solvent diffusion, you realize that this is the result that Kramers would have predicted if he'd had at hand and invoked the actual results on diffusion coefficient or transport versus viscosity. Namely, there's a low viscosity behavior and a high viscosity behavior, and here you are seeing them for one more time. Segmental reorientation times are also sensitive to the local polymer concentration. Here we see an example of this for center-labeled polyisoprene, work of Johnson et al. The open circles show the time constant for reorientation of the center label on a long polyisoprene chain. The filled circles show the same dye, this time as a small molecule in the same polymer solutions. We see that both relaxation times increase very dramatically as the polymer volume fraction is increased from 0 to 1. The relaxation time for the center segment of the polymer increases by 2 orders of magnitude. The reorientation time for free dye molecules increases by 3 orders of magnitude. There's no indication in this graph of a dramatic discontinuity in the slope or in the reorientation time itself, but both times clearly increase with increasing polymer concentration. It's also possible to change the concentration of chain segments near the center of the molecule, that's where the chromophore has been inserted, by changing the solvent quality. As you increase the solvent quality, the concentration of chain segments near the chromophoric label you've inserted in the polymer chain will tend to fall, and corresponding to that, the relaxation time is indeed observed to fall. You'll have to read my books to find the detail on that.